Very good morning. In today's lecture, we can see uh, general CRLB for signaling white Gaussian noise with an example. Okay. In the last class, we have been discussing uh, the Fisher information theorem, that is I of theta. That is the continuation of a CRLB theorem. And in this, we will discuss one an example for a general CRLB for signaling white Gaussian noise. Here we will consider one observation, that is x of n is nothing but s of n theta plus w of n, where where we are assuming the observation as a deterministic signal, that is s of n theta will be a deterministic signal with an unknown parameter theta that is being observed in the white Gaussian noise. That means we are considering a deterministic signal that is being with an unknown parameter theta that is being observed in the white Gaussian noise. So we can let me start with that example. Okay. So consider the observation. Let the observation be x of n equal to s of n theta plus w of n equal to 0, 1 to etc. n minus 1, where s of n theta is a deterministic signal. You just underline that word, deterministic signal, and theta is an unknown parameter that is being observed in the white Gaussian noise w of n, and w of n is white Gaussian noise. Okay. So as in the general case, what we have been discussing in the previous example also, we are considering that probability density function. Afterwards we are taking the natural logarithm of that one. We are considering the first derivative of that natural logarithm of that probability density function, and again we are taking the second derivative of that probability density function, and further we are calculating the variance. Okay, we can see that one. The solution for this one. As we know, we have p of x theta is nothing but p of x of 0, x of 1, etc., etc., x of n minus 1 of theta. In general, I can write this in the form of p of x of 0 of theta, x of 1 of theta, x of 2 of theta, etc., etc., x of n of theta. Okay, that is p of x of 0, x of 1, x of n, etc., etc., x of n minus 1 of theta can be rewritten in the form of p of x of theta, p of x1, x of x1 of theta, etc., etc., p of x n of n minus 1 of theta. Sorry. So since the samples are independent, I can write this in the form of pi, that is p of x of theta is nothing but pi, capital Pi, n equal to 0 to n minus 1, p of x of xn of theta, which I can write it as pi n equal to 0 to n minus 1, 1 by root of 2 pi sigma square e raised to minus 1 by 2 sigma square into x of n minus theta, that is s of n theta, s of n theta. Okay, x of n minus s of n theta, that is p x of theta equal to pi n equal to 0 to n minus 1, 1 by root of 2 pi sigma square e raised to minus 1 by 2 sigma square x of n minus s of n theta. Okay, whole square. Okay, x minus theta mu the whole square. So I think up to this it is very clear for you people. That is the general things what we have adopted in all other examples also. Okay, you can see the next case. Sorry, p of x of theta, that I can in general I can rewrite this as 1 by 2 pi sigma square n by 2 e raised to minus 1 by 2 sigma square sigma n equal to 0 to n minus 1 x of n minus s of n theta the whole square. Now we will take the natural logarithm of this one. So once we are taking the natural logarithm of this one, I can return as minus ln into 2 pi sigma square raised to n by 2. Exponential term will be gone. It will be minus 1 by 2 sigma square sigma n equal to 0 to n minus 1 x of n minus s of n theta square. Taking the natural logarithm, p of x of theta equal to minus ln of 2 pi sigma square n raised to n by 2 minus 1 by 2 sigma square. The exponent term will be gone. If we are taking the natural logarithm, x of sigma n equal to 0 to n minus 1, x of n minus s of n theta the whole square. Now we will take the first derivative of this one. Once we are taking the first derivative with respect to theta, the first term will be 0, that is minus ln of 2 pi sigma square raised to n by 2 will be 0 because there is no theta term. Okay, and the second will be minus 1 by 2 sigma square sigma n equal to 0 to n minus 1, 2 into x of n minus s of n theta minus of dou by dou theta of s of n theta. Since derivative of s of minus s of n theta is nothing but dou by dou theta of s of n theta. Okay, that is for taking the first derivative. Dou by dou theta of ln of p of x of theta equal to 0. First term is 0. I am not writing that one. Minus 2 sigma square sigma n equal to 0 to n minus 1, 2 into x of n minus s of n theta into dou by dou theta of minus dou by dou theta of s of n theta. Okay, so 2 and 2 get cancelled. Minus and minus will be positive. I am taking the minus dou by dou theta of s of n of theta, that is minus a, and I am taking the outside the sigma. So minus and minus will be positive. Sorry. Dou by dou theta of ln of p of x of theta will be 1 by 2 sigma square. Minus and minus is positive, so I have not written that one. So one more step I will write as 2 into x of n minus s of n theta dou by dou theta of s of n theta. Now 2 and 2 get cancelled. You will have 1 by sigma square sigma n equal to 0 to n minus 1 x of n minus s of n of theta dou by dou theta of s of n theta. Okay. S of n theta. Now you see, if you are taking the second derivative of this equation, the last equation, that is 1 by sigma square sigma n equal to 0 to n minus 1 x of n minus s of n of theta dou by dou theta of s of n of theta. The two term, that is x of n minus s of n of theta and dou by dou theta of s of n of theta is the two term contains the theta term. It's not. So if you are taking the derivative of this one, this is in the form of multiplication. Derivation with respect to multiplication, that is d by d theta of AB must be equal to a into d by d theta of A into B plus a into d by d theta of d by d theta of B, like that. Okay, or x dou by dou x of that, I think you know that one, that taking the derivation with respect to multiplication. Okay, so similar to that, I will take this one. I will take the second derivative of this equation, and what I will do is I will take the 1 by sigma square outside. So this will becomes dou by dou theta of x of n minus s of n of theta into dou by dou theta of s of n of theta. That changes to minus dou by dou theta of s of n of theta into dou by dou theta of s of n of theta plus x of n minus s of n of theta into dou square by dou theta square of s of n of theta. Okay, or dou square by dou theta square s of n of theta. Okay, so that changes to dou square by dou theta square ln of p of x of theta will be equal to 1 by sigma square sigma n equal to 0 to n minus 1 2 in there is no 2 minus dou by dou theta of s of n of theta dou by dou theta of s of n of theta, because x of n is 0, so only one term is there, that is minus dou by dou theta s of n of theta. The second will be x of n of s of n dou square by dou theta square x of s of n of theta. Okay, this is the case. Now what we will do, I have to take the expectation of this one, which changes to expectation of 1 by sigma square sigma n is equal to 0 to n minus 1 of the corresponding term. Okay, expectation of 1 by sigma square sigma n equal to 0 to n minus 1 minus dou by dou theta of s of n of theta dou by dou theta of s of n of theta plus x of n s of n of theta dou square by dou theta square of s of n of theta. In this time, if you are taking the expectation inside that bracket, that inside sigma, we can consider uh, the first term. So I will take the minus term outside, that is minus 1 by sigma square, sigma n equal to 0 to n minus 1, expectation of dou by dou theta of sine n of theta into dou by dou theta of sine n of theta, that is nothing but dou by dou theta of sine n of theta the whole square. In the second term, if you are taking the expectation of x of n minus Sn of theta, dou square by dou theta square Sn of theta will be changes to 0. How? Because expectation of x of n minus s of n of theta, x of n minus s of n of theta is obtained from the can be obtained from the that is the example, that is from the given observation, because observation, in the given observation, it has given that x of n is nothing but s of n of theta plus w of n. So x of n minus s of n of theta will be equal to w of n. Since the in expectation of w of n is nothing but 0, we can take expectation of x of n minus s of n of theta is nothing but expectation of w of n, that is nothing but 0. So if you are taking the expectation of x of n minus x of n of theta, that is nothing but expectation of w of n, that we can take, that term we can take it as 0. So 0 into dou square by dou theta square sine n of theta, that is why the second term becomes 0. Okay, the same procedure I am adopting here. Dou square by dou theta square ln of p of x of theta will be equal to x minus 1 by sigma square, sigma n equal to 0 to n minus 1, dou by dou theta of s of n of theta the whole square plus 0 into, how it comes 0? Because expectation of x of n minus s of n of theta is nothing but expectation of w of n. Since expectation of w of n is nothing but 0, I take a 0. So the second term will be 0. Finally, you will get dou square by dou theta square ln of p of x of theta is nothing but minus 1 by sigma square, sigma n equal to 0 to n minus 1, dou by dou theta of s of n of theta the whole square. Okay, so our variance of theta cap is that should be greater than or equal to 1 by minus of e of expectation of dou square by dou theta a square ln of p of x of a. That is variance of a cap. Variance of a cap is nothing but variance of a. I have written one mistake here. In general equation, it has given variance of a cap, that is greater than or equal to 1 by expectation of dou square by dou a square ln of p of x of a. Here instead of a, it is nothing but theta. Okay, so what happens means I will just take the expectation of dou square by dou theta square ln of p of x of theta is nothing but 1 by sigma square, sigma n equal to 0 to n minus 1, dou by dou theta of s of n of theta the whole square. So minus and minus will be can cancel, it will be positive, sigma square will be in the numerator, so it will be sigma square divided by sigma n equal to 0 to n minus 1, dou by dou theta of s of n of theta the whole square. That is nothing but variance of theta cap. Sigma square divided by sigma n equal to 0 to n minus 1, dou by dou theta of sine n of theta the whole square. So this is nothing but the general CRLB for signaling wide Gaussian noise. We have calculated the variance of theta. So from this we can have a note that if the derivatives in the denominator has larger value, then your RHS will have a small value. Okay, the derivatives in the if the derivatives in the denominator have a larger value, then the right hand side will have a small value. Thus the signal that change rapidly with the unknown parameter will result in an accurate estimator. Okay, that is a note what I had to take down. That is, if we note that if the derivatives in the denominator, if the derivative in the denominator has larger value, the RHS will have a small value. Thus the signal that changed rapidly, small value, thus the signal that changed rapidly with the minimum parameter result in accurate estimation rapidly with the unknown parameter theta result in accurate estimation. Okay, so this is a general thing. Just take it in the underline that variance of theta cap, that is one of the important relationship. If you know the dou by dou theta of sine of n of theta, you can directly substitute in this one. Okay, so we will just see one example, a general example. I will not explain all this thing. I will just take only the variance of theta. Okay, variance of theta, the equation for the variance of theta, and directly substitute, and we can see the we can see whether the unknown parameter will result in an accurate estimation or not. Okay, just one example, that is sinusoidal frequency estimation. Sinusoidal frequency estimation. Okay, I will give you the observation for here. Let observation is, let S of n of theta is nothing but a into cos 2 pi f n of n, f naught of n plus 5, where f naught, it should be in between 0 and 1 by 2. Okay, 0 less than or equal to f naught, less than f naught less than 1 by 2, where your amplitude A and the phase are known, that is A and phi are known, and use the expression for the general CRLB to find the values of variance of theta, variance for f naught. That means here the amplitude A and phase phi is known for you, but you have to calculate you have to find the general expression for the general CRLB in order to find the variance of f naught. So our final thing is to calculate the equation for variance of f naught cap. Okay, so we know where amplitude and phase are known, and use the expression, that's one note for you, expression for general CRLB to find variance of f naught. You can see the solution for that one. Variance of theta cap, you know the equation for that one. Just now only we have derived that one. Theta cap should be greater than or equal to sigma square by sigma n equal to 0 to n minus 1 dou by dou theta of sine s of n of theta the whole square. Okay, now what we will do, we will take the derivative of the given observation. You know the derivative of cos theta is nothing but minus sine theta. So here theta is nothing but f naught. So I will take a variance of f naught cap is nothing but sigma greater than or equal to sigma square, sigma n is equal to 0 to n minus 1 dou by dou f naught of s of n of f naught. Sorry, one mistake what I have done is, in the observation I have given let s of n of theta, it is not theta, it is f naught. Okay, you just change that one, it is f naught, that is s of in the observation I have given s of n of theta equal to a into cos 2 pi f naught of n plus 5. Instead of theta, you just change it as f naught. I think now it is clear for you. Okay, so now what I will do is, I will take the derivative of a of cos 2 pi f naught of n plus 5, which is nothing but dou by dou f naught of s of n of f naught. Okay, dou by dou f naught of s of n of f naught is nothing but minus, because the derivative of cos theta is minus sin theta, minus a sin 2 pi f naught of n plus 5 into 2 pi n, because with respect to f naught only we are differentiating, so it will be 2 pi n. Okay, it is clear now. Now what I will do is, I will just rearrange this one, that is dou by dou of theta of s of n of theta is nothing but a into, sorry, I have to take the square now, dou by dou f naught of square I have to take. So what I will do, a square into 2 pi n sine 2 pi, because in the variance it is a sigma square by dou theta of s of n of theta the square. So different, we are taking the differentiation of this one, that observation. Now we have to square for that one. It is not double, it is not second derivative, it is only squaring that the first derivative. In the general case we are taking the second derivative, we are not doing that one, but only we are squaring the first derivative. So it becomes a square into 2 pi n sine 2 pi f naught of n plus pi the whole square. Okay, now we could take that is sigma n equal to 0 to n minus 1 dou by dou f of sine n of s of n of f naught is nothing but a square into sigma n is equal to 0 to n minus 1 2 pi n into sine 2 pi f naught of n plus 5 the whole square. Okay, now variance of f naught cap should be greater than or equal to sigma square by a square one more mistake I had done, not dou by dou f of s of n of theta, the s of n of f naught the whole square, that is the general equation for the general CRLB. Now it changes to implies variance of f naught cap should be greater than or equal to sigma square by a square sigma n equal to 0 to n minus 1 2 pi n sorry for here, because I have done one more mistake here. I have taken 2 sigma, so only 1 sigma is required. Okay, I just copied that first equation here only. So just a small correction is that instead of 2 sigma you write only 1 sigma. Okay, I think now it is clear for you. So I am just plotting the CRLB is plotted with respect to frequency for an SNR of otherwise I will change here itself. This thing is not required. Sorry, anyway you change it. Okay, so this the first sigma is not required. You just delete that sigma. Okay, sigma n equal to 0 to n, because I have written 2 sigma here, only 1 sigma is required. Okay, sigma n is equal to 0 to, because that is the general equation what you have find it. Sigma n equal to 0 to n minus 2, you just delete that one, only 1 sigma is required for in this case. Okay, so here the CRLB is plotted with respect to frequency for signal to noise ratio of a square by sigma square equal to 1. Okay, a data record of length n equal to 10 and phase of phi equal to 0. So the plot is just like this one. You can see that this is a plot of Cramer lower bound with respect to frequency. So here I have taken the a square by sigma square equal to 1 with the n equal to 10. This the figure that I had taken directly from the textbook for phi equal to 0. So it is noted that there appears to be a preferred frequency for an approximation as f naught tends to 0. As your f naught is frequency is being tends to 0, you can see that one. The CRLB goes to infinity. You can see that it becomes infinity. Okay, this is because f naught is close to 0. A slight change in the frequency will not alter the signal significantly. So the derivative with respect to f naught has a small value in this case. Okay, thank you. Now we can see in the next example something regarding what you call as extension of CRLB to a vector parameter. Thank you.